All right. Hello, everybody, and welcome back to another session of virtual welding. Um, when we talked last week, many of you were sending messages on the group chat and that were questions, and that helped me also to get a sense of feedback and to give an answer in real time to questions that might have come up. So if you wish to use it, whether you send me a private message or a message to everybody, that's very useful. So if you have any other comments about the class, about the pace, too fast, too slow, if the material uploaded can be done any better, please let me know. I care a lot about it. And I'm trying everything I can to do it as good as possible. For those among you who are proactive and downloaded the files earlier, I did an update just a few minutes ago. So none of the changes are big and they are all uploaded. But if you wish to get the latest material, it's been just updated just before the class. All right. What we are going to discuss today is the name of things in welding. And there will be two main topics. One, it will be welding terminology, large, and the other will be about welding symbols. And both are essential because they are the language we speak. So we wouldn't be able to discuss things that are of any depth if we couldn't name the parts of the weld or name the welding procedures or to name the tools used. Now, this is essential, this is important, but to some extent, today's class essentially will be like reading a dictionary, and that doesn't sound like a lot of fun. So I'll try to do everything I can to make this class as engaging as I can. But the point of today is pretty much reading a dictionary, and then the welding symbols is like reading a foreign alphabet, in which, of course, I'm going to discuss a few things, but then you need to prepare on your own, sit down and go over the examples. The good news is that about all of this, you have the previous exams in which you see the type of questions I used to ask. And it will be this year, although the exams will be done online, will be much the same. And so let's get started. So about welding. What I put here is if you look at the Lincoln Procedure Handbook, the one, oh, by the way, about the book, if please get in contact with Alejandro, our teaching assistant. He's coordinating the purchase of books for the whole class. And you need this book, and it's a really good book. So in this book, section 16, chances are that you don't have it yet, but so you know when you prepare, in section 16, there is lots of terminology. And also there is an AWS standard that is essentially a dictionary. And that costs money. But at U of A, these standards, you can access them for free. And I really recommend you do it. You get it, it's money in the bank when you have a job. Well, for later when you have a job. This terminology, I know that some in this welding class have a significant exposure to welding. So this will be like tell you what is a table and what is a chair that you already know. But not everybody does, right? So let's go and let's try to get everybody on board. So some very basic welding terms we're going to be using, and I didn't put them in alphabetical order or in any way other than how I thought it related to each other. So when you weld, you're moving the torch, and as you move the torch, you move it at certain speed. Okay, that is what is called the travel speed. But it's not the only speed in welding, because when we have a process in which we feed a wire, some of you might know exactly what I'm talking about, and some other of you will know everything about this in a couple of weeks from now. So when you feed the wire, you feed the wire at a certain speed. So now you have two speeds, the travel speed and the wire feed speed. When you do arc welding, or pretty much when you do arc welding, the electricity comes from these cables that are called the leads, right? And they run from the power supply to the torch. And now there are other terms, and as I do this here, that's okay. You'll see that some terms in welding, many people use the same words, but they mean different things. So, of course, as you take this class, we will have an official meaning for each word, but we should be aware that as you talk with other people, sometimes you might want to make things clear. One of those things is arc length, right? And we're gonna define arc length when you have an arc as the distance between the surface of the weld you're making and the surface of the electrode. When we discuss the physics of the arc, and when we discuss arc welding processes in detail, you'll see that although this definition is fairly clear, there are many other ways in which we could define it, and and people indeed use the same words for different things. DC. DC means the current flows in only one direction, and typically means it's not only in one direction, but it's also constant, right? And if the electrode is negative, we call it DC electrode negative, and if the electrode is positive, you see DC EP. Sometimes the current goes in both directions. That means we have AC going both ways. So that's also called variable polarity. That is some word that I should add to this. In the old times, there was a naming convention that I don't recommend, but is still used by many, that they call straight polarity to electrode negative. And this is for historical roots. For example, in MIG, you don't use straight polarity. You use what is called reverse polarity, that is electrode positive, right? Things to know. Constant current, CC, means that the electrical, the power supply you use, the electricity, will give you a current that is more or less constant, even if you change the voltage. Conversely, some other power supplies give you more or less constant voltage, even if you change the current. And we can relate to this. For example, an electrical outlet, for example, in this office to where this computer is plugged, that is 110 volts. And it's 110 volts whether I'm drawing very little current or whether I connect my clothes dryer, right? That is a lot of current. So this has interesting implications, important implications for the stability of the process. So in some process you use one type and in some the other. I'm not going to discuss now the why, but for example, in this process, GTAW or TIG, which right now you don't know exactly what it is, but all of you will know everything about it by the time of our first quiz, or this other one is stick welding, we use constant current for good reasons, which we will discuss. But in MIG or flux core, we use constant voltage, and the current can change, but the voltage is constant. We can also have advanced waveforms, and these advanced waveforms typically are proprietary. And when things are proprietary, people try to come up with their own cute acronyms that would help identify, make them unique in sales. We have Lincoln has STT, which we will discuss in detail. Miller has RMD. Fronius has CMT, and something very interesting, Miller also had something called CSC that preceded this other CMT from Fronius. Whatever these are, it's impossible that all of these things make sense to you now, but I want to plant the seed of words we're going to be using farther down in the class. Other terms, preheat. Sometimes when we weld things, we want them hot for good reasons, and we'll see all the physics and math of that later on. But the bottom line is that is called preheat. Now, between two passes, after I weld, things tend to be hot, right? And if I keep welding, it gets hotter and hotter and hotter often. So between pass and pass, we have what is called the interpass temperature. And that matters. For example, if I have a high preheat and I weld, my weld might not put enough heat, and actually things start to cool down and we might need intermediate preheats. On the other hand, for example, in the case of stainless steels, if I start to accumulate heat, my interpass temperature starts to raise, and I need to stop welding until things cool down, because otherwise I can ruin the alloy. Right now, these are only words. All of these come associated with physics and metallurgy concepts, which we will discuss. Talking about temperatures, there is also this thing called PWHT, post-weld heat treatment. For example, if a weld, for whatever reason, is too hard, there are ways of making it softer by doing, for example, a tempering treatment, or we can also relieve stresses. So many things that can be done after welding, but we need to know ahead of time that this is the way we're going to go about it, and it has a name. Two more acronyms is PJP and FJP, partial joint penetration and full joint penetration. When we discuss symbols later today, we're going to see exactly what we mean by this. Some more words, and I'm going to mention some of these, but I cannot go over all slides in detail. But you must know all these things, right? So something called the wire cast and helix. And these are things that are fascinating concepts, because from my ideal point of view, you can look at the physics and talk about the electrons as we will, and we believe we understand. But then reality is a very different thing. For example, if we are having a process that involves wire, we feed wire into a system. But guess what? The wire somehow has to come coiled, right? And when the wire is coiled, that means it's bent. And when we uncoil it, it doesn't necessarily go straight, right? And this can bring us problems, because if the wire is not really straight, the tip of the electrode might start moving around as the wire melts. So there are two concepts associated with how straight the wire is. One is the cast, and the other is the helix. So if I get the wire out of the spool, I can cut a loop of this wire and toss it on the floor and see what happens. And two things are going to happen. One is the wire is going to make more or less a circle, right? And the diameter of this circle is what we call the cast. And of course, if I have a very small, tight cast, it means the wire is very curved, and the chances of problem are higher. If the wire pretty much opens in a huge circle or pretty much straight, then I'm in a better shape. And the other is the helix. If you toss the wire on the floor, it's not going to go flat. The wire is going to end up with the tips somewhat raised. And how much the tips are raised when we cut a loop of this wire? That's what we call the helix. And similar to the cast, it is all about how straight the wire is, or how tightly coiled it was, and what the problems it can bring when we weld. Funny enough, people care about this. And for example, the manufacturers often do a pre-twist of the wire, such that when you unspool it, and unspools straight. And when you buy wire, the different quality of wires include things like the cast and the helix. And this is fascinating because we would have thought that a good wire had just a good alloy or maybe a good surface termination. But no, not only has a good alloy, has a good surface finish, also has these small, these also ends pull straight with the cast and helix that are adequate. More welding terms. If we make a weld in one pass, guess what? We call it a single pass weld. And if we need many passes, for example, if we're welding something that is really thick, for example, a 4-inch thick, 100 millimeter thick plate, for sure we need many passes. And we will see the reasons for that. But if we have many passes, then interesting things happen. It doesn't seem like that much, but for example, in a single pass weld, if the plate was a little bit dirty, I can put some magic spice in my electrode that will clean up this dirt, right? That can be silicon or can be manganese. We will discuss all this later in the metallurgy section. But guess what? If I have a multi-pass weld, the first pass might be a little bit dirty, but the second pass is fairly clean because it's on top of my previous weld. It didn't get to oxidize or get dirty somehow. And so some electrodes are good for single pass welding. Some electrodes are for multi-pass welding. Isn't this interesting, right? And again, if we idealize things, everything looks very simple, but in reality, there are all these subtleties. Right now, we're only planting words, just saying words so you become familiar and you need to remember them or have them handy for your exam. But people use these words speaking all the time, and they have this deeper meaning, not just one or many. Tack welds, right? When we are putting something together, it doesn't really stay together. So what often people do is put some small welds such that it doesn't move anymore. And why this matters, because as we weld, and we're going to have 1 or 2 lectures on this, the thermal expansion creates distortion, so everything moves. If you don't want it to move too much, you have to clamp it very much. Sometimes you tack it, right? And again, this is such an important concept. If you look on the Welding Precision Handbook that you're gonna get soon, it talks about how you have welders and you have tackers. So some people are certified to do tacks. So if you're not certified, you cannot even do tacks. But if you cannot qualify really as a welder because you're only starting, you can get a certification for tacks. Quite interesting. More welding terms. If you weld straight, that's called a stringer bead. And if you like move left and right, left and right, left and right as you weld, that's called a weave bead. And who knew? This is so super important. If you think in a straight bead, you move relatively fast. So the amount of heat you put in welding is distributed very quickly, right? And these welds tend to cool down fast. We will see all the formulas for this, and we'll understand the implications for steels and aluminums and everything. So stringer bead, for example, in stainless steels, often you want these stringer beads, right? Weave beads are good when you have a pretty poor joint preparation and you need to gap a bridge, or when you have a problem that if the weld cools down too fast and then it's too hard, if you start weaving, you start putting a lot more material that will take longer to cool down, and the weld will be a little bit softer. This is so important, right? And the way also, and by the way, I make a clarification. I'm an engineer. I'm not a real welder, but if you talk with the real welders among you, they'll tell you all the details about weaving and how you make sure that the edges of the weld are proper. if you look at the cross sections, this is interesting. You get to see the stringer, the cross section of the welds, right? And you see they look like fish scales. But if I look at a cross section of a weave bead, you see this very wide weave. This is a really wide weave, right? Another type of weld is the stitch weld. This is good to reduce residual stresses. It's good in many aspects, especially in civil construction, right? And you get to see the stitches. And there are special symbols for these stitches. Some more about welding weaves. I'm not going to dwell long on this. I just wanted you to see that the weave was not just going left and right, as I mentioned. It's much more sophisticated than that. And I did my own search, and I found these weaving techniques, but there are many more, and they have like funny names. I don't understand them, and I don't know all of them. But please know that there are many types of weaves. And if you look again at the Lincoln Procedure Handbook, it will say how different welding positions, whether it's flat or vertical, you want to have different types of weaves. And they tell you which ones to have. And these weaves, I don't think those are like everyday weaves. They look more like artistic weaves, but I think they are so awesome that I wanted to share these with you, right? You can totally tell how they were weaving here, right? And in this case, this finish is called a stack of dimes. And this is an aluminum weld. They don't tell me, but this much I know. I can tell because the cleaning action around it. And this is with a pulsed program. And every time the torch pulses, creates a weld pool that looks like this stack of dimes here, right? So about weaving techniques, the Lincoln Procedure Handbook, I made these notes here. When you have the book, you can check it out. More welding terms, the torch angle. And some of these things I didn't mention last year, but we have a student doing his Master's of Engineering in the lab, his MEng, and he transcribed every single procedure that appears in the Lincoln Procedure Handbook into Excel and started to analyze them with the tools you are going to learn later on in the class. And the Lincoln Procedure Handbook specified torch angles. And so I decided to include this slide in which we have, when you make a procedure, you have to say what your torch angles are gonna be. So if you're welding in this image that I'm highlighting here, from left to right, as you move in the direction of the blue arrow, if the torch points backwards, is what we call backhand welding, or having a drag angle, and that is specified in the procedure. And conversely, if I'm welding from right to left in this image on the right, if I'm welding from right to left, the torch is pointing somewhat to the front, that is called a push angle or a forehand angle. And these have very important implications in practice, and they have very important implications when we study some of these mechanisms present in the weld. Now, imagine you're welding, making a fillet weld, and you'll know soon what fillet welds are, right? And then you have the work angle. Of course, in a fillet weld at 90 degrees, sometimes you want to have 45 degrees. This makes sense, but it's not always. And if you look at the Lincoln Procedure Handbook for fillet welds, you'll see that sometimes say you should have different angles other than 45. Sometimes you should aim the torch a little bit more towards the top part or the bottom part. They mention all those things. I mentioned briefly the term weld pool. And I had mentioned this last class too, when I mentioned that welding is a non-equilibrium problem in which we melt some, but we don't melt all. And that is really tough. Melting everything is easy, and not melting anything is easy. But just melting what you want and not more and not less, that's difficult. that molten part that is so carefully crafted, and for steels, it works exactly as we want, just out of a miracle. That little molten part is what we call the weld pool, or weld puddle, or the weld bead. Here we have an image. Actually, this image was part of the slides of last class, right? This molten part, that's the weld pool. Another term is called the keyhole. So imagine you're welding with a laser, right? And when you weld with a laser, the laser kind of drills into the metal and moves on, right? And the same thing happens with electron beams. The same thing happened with electron beams. And the reason I mentioned keyhole here is because when welders use electrode 6010, whatever it is, you're gonna learn, it's a cellulosic electrode, but it has a very penetrating type of arc, and they tend to call it the keyhole. But it's a very different animal than this other keyhole for electron beam welding. So I just wanted to introduce the term, and we'll get deeper into that later on. We mentioned tags. Here the tags are here. Here we have some spatter, typically it's bad. But again, if you take a look at the length and procedure handbook, spatter is never pretty, but sometimes it disqualifies your weld, and sometimes it means nothing. So whether spatter is good or bad, that depends on the application. Good or bad, there's pretty much nothing that is intrinsically good or bad in welding. Is it fit for purpose or not fit for purpose? So spatter, nobody likes it, but sometimes it doesn't matter, and you don't remove it. Other welding terms. For backing plate, when you're making welds that are relatively big, the molten metal can drip and fall. So you put something to catch it. And that is what is called a backing plate. And there are many ways of making a backing plate. For example, if you're welding steel, you can have a little steel plate that will prevent it from dripping through. Now, this steel plate might melt, and then you never get it out. That's what is called a permanent backing strip. I'm going back to the concept of fit for service. Pretty? No, it's not pretty. But if it doesn't matter, it doesn't matter. And you leave it there. You can have, for example, a copper backing bar, and the copper has a very high thermal conductivity, so it's going to chill the metal on contact and give you this really good looking reinforcement, and it's going to prevent from the weld from dripping through. If not copper, you can use ceramic backing bar that is not going to melt because of the high melting temperature of the ceramic. Here I have a photo of electrodes, and these electrodes, these are a particular type of welding, and then we call this stick welding colloquially. And what you get to see is a steel rod, and then you see something on top of it. This something on top of it we'll discuss in much detail, but it's called the flux, and it's a mixture of powders and agglomerants that make the weld have most of the welding process have most of the features it has in this type of welding, and comes from this flux. This flux during welding, part of it or all of it melts. And when it melts and then goes solid, you have this little, you have this little coating, these shells, right? And these shells is the same flux that melted and went solid. But now we don't call it flux anymore. We call it slag. And if you ever saw a welder in action, when they come with a hammer and they start hammering the weld, what they are doing is chipping off this slag that is a solidified glass, right? It's a ceramic. So it chips off and goes away, and here you get your weld, right? So same thing. Before you melt it, you call it flux. After it melted, you call it a slag. It's not exactly the same because there are some chemical reactions that make this have a slightly different composition than this other here. We don't need to worry about this now, but I do expect that when we say flux or slag, you'll know exactly what we're talking about. And then we can discuss about the subtleties of the mechanisms present. Unfortunately, you're not coming soon to our lab, but I do hope that someday you'll come and you'll get to see all these things. We have a manipulator that is something that moves the torch left and right and up and down, right? Now, this is good for making welds that are in the flat position, but if you need to weld a pipe, and the pipe sometimes you weld on top, sometimes on bottom, so you have two choices. One choice is you rotate the pipe such that you're always welding on top. And in that case, what you have is a positioner. The way I remember the positioner is because the positioner puts the pipe in the position you like, right? And you'll see, actually, if this is not from our lab, this is exactly the same as we do. And then other type of welding is called orbital. If you needed to weld a cylinder, and you cannot rotate the cylinder, for example, in the case of a pipeline or the case of very large vessels, and what you do is you rotate the weld. An orbital welding can be at sizes from tiny to huge. So look at this image here on the bottom left. This is sealing the tubes for a heat exchanger. And because many of you took heat transfer with me, you recognize this is a shell and tube type of heat exchanger. And here the tubes through which one of the fluid goes, and then the shell is the fluid that goes in between the tubes. In the case of nuclear power plants, I've been in France and I saw how they make it. A single heat exchanger might have thousands of these. You don't do those by hand. You do those with a machine. But just welding them and inspecting them at such high level of responsibility, you have a lead time of a year. So if you say, I want to make a nuclear power station and I have the drawings, you go to a shop and they'll say, well, I'll start tomorrow, come next year, because of how many of these needs to be done. And orbital welding can be done at very large sizes too, right? In this case, you put a track and you have like a little bug that goes moving the welding torch all around. We have all three of these in our lab. More terms about welding. I'm not going to get into all the details, but this process here in which the welder is holding this stick electrode, this is called manual. Everything is done by hand. Now, if you change it and you have a process like this, in this case, the welder is doing MatE. In this case, you have the wire is being pushed by a motor. We'll see all the details about that later on. But now, although you do everything by hand, the feeding of the consumable is done by a machine. So they call this semi-automatic, right? My mind is pre-manual, but it's less manual than this other process of up here. So we call it semi-automatic. Now, when I put my welding torch in one of those little bugs I discussed, for example, for the case of orbital welding, that is called mechanized. And now if the bug is somewhat intelligent, like for example, a robot, now we start talking about automation and different levels, automated welding, robotic or adaptive. American Welding Society went all too happy in defining all these, but once you start having feedback loops, we have a fairly advanced level of automation, whatever we call it. All of these we have in our lab, and I hope you'll come see them at some point. this is just words, but these are important words, and these words are going to come up again when you have our lectures on codes and standards. One is called the procedure qualification record, and the other is the welding procedure specification. If you remember our first class, when I made an analogy between welding and music. I said the welder is like a musician, and the welding engineer is like a composer that says what note to play when and how. Well, in music, you transmit that knowledge through a music sheet, right? In welding, you transmit that knowledge through the welding procedure specification that says how many volts, how many amps, what travel speed, what wire feed speed, all those type of things, right? And so please know that this WPS, right, is the equivalent of a music sheet. And if you weld without a WPS, you are probably welding in a farm. But if you're welding a pipeline, you better follow the sheet. The other word is procedure qualification record, and PQR. And the PQR, what it says is how, based on what you determine this WPS. So a musician makes a music sheet, but doesn't need to tell anybody why he chose those notes. But in welding, we do. Because if the bridge falls, we engineers have to say, look, I recommended we weld it this way for these reasons. And here are the tests we did, right? And you would record what welds were done, in what material, in what conditions, and you do whatever test you need to qualify, bend test, tensile test, or hardness, whatever it is. Now, as you can imagine, you better do your procedure qualification record before you do your WPS, right? Because otherwise the welder is going to be welding and you don't know if the weld is good or bad. So I don't know, I've been in meetings of our welding societies in Edmonton in which the running joke is about people writing the WPS before the PQR, right? And at the beginning I was like, what's the story? Well, now you would be into the joke. Like if you write the WPS before the PQR, you might be up for big millions of dollars losses, because if actually you cannot qualify the weld you specified, somehow you'll need to remove all the welds and re-weld again. It's not a happy thing. And by the way, it happens. But it's half a joke and half a sad truth. Okay, in this slide here, you have a million acronyms, right? Which doesn't mean a whole lot to you right now. The funny thing, they're gonna make a whole lot of sense to you very soon, and you're gonna know exactly what they are and how they work. We're gonna learn about these processes. So I don't mean to put this here to scare anybody. This is just the language. At least you have them all in a list, and you're gonna see when we discuss welding symbols, when we discuss welding symbols, how that we use these acronyms here. Weld joints. Weld joints, and if you look at all the exams, you're gonna see we use these. We use these concepts quite a bit. When you put the two plates edge to edge, we call it a butt weld. If we put them side to side and we weld on the edge, we call it an edge weld. When we are welding in a corner from the outside, that's the corner weld. When we overlap them, but we fill on the edge of the overlap, that's a lap weld. And then when we have a T joint and we fill in inside this corner, that's what we call a fitted weld. And then we have joint preparations. We have these 5 types of joint configurations, and then we have joint preparations. We have, if it is a square cut, very cheap, square. If we have a bevel, right, single bevel, if we have bevel on 2 sides, we call it V, right? And if we have a double bevel, is when we have a single bevel on each side of the plate. We can have a J, can have U joints. Again, reading a dictionary. Oh, okay. Thank you, Eddie. Like here with the message to everybody is that about a WPS could be supported by multiple PQRs, and Eddie has been working on that now for long. So interesting things. Yeah. So more about these weld types. Let's see. So if we have some types of weld, you weld on top of a plate, right? And we do this a lot for research. And this is called bead on plate, when you just don't put 2 plates together, but you just deposit the bead on top. FJP and PJP, we had discussed earlier on. And here we have an example of complete joint penetration. And here we have a partial joint penetration. So more types of welds. This is called a plug weld, in which you weld, either you melt the top plate until you melt the bottom plate, or you just make a hole. Surfacing welds. There are all these different types of welds. I want to go quickly about some considerations when we talk about joint preparations. For example, if we have a single bevel joint, we can make that with a grinder, or we can cut it with a torch. So this is relatively easy to do, right? Now, if you cut this, that was very good, very cheap to do, then you need to fill it up. If the thickness of the plate is not very high, you're happy, you don't really care. But if the thickness of the plate was quite thick, then you end up putting many passes, hundreds of passes on occasion. Now, if you use a double bevel preparation, you can show with math that the number of passes, the amount of filler you need, is about half of what you needed here for the same bevel angle and the same plate thickness. And has many advantages, because if this is symmetric, it's going to have less distortion, because however the weld pulls more or less the same in both ways. And it's still easy to make. Now, it is a pity I don't get to see you guys, but if you were to say, okay, why don't I always do a double bevel joint preparation, given the advantages? There are good reasons. For example, if we are making welding pipe, unless the pipe is very big or the welder is very small, you don't get access to the inside. So the access we might have into a weld, either because it's in a pipe or because it's in a closed box, determines whether we can have this 2-sided joint preparation, or we have to stick with a single-sided joint preparation. And here we have a J joint prep. So the J joint prep has a cool advantage that gives you room to work at the root, right? But it doesn't keep opening. If you need good room at the root here, you would open up the bevel, but then you need to fill up a lot. With a J groove, you have room at the root, and you have fewer passes. So this, to some extent, the J groove is better than the V groove, the single bevel. Yet there comes at a price. I could do the bevel with the grinder or with oxy-fuel cutting. This one, I need to machine. So the way we make decisions in welding about what to do is not just what is best, because best is ill-defined. Maybe I have the tools to machine this in my shop, and I'll be a happy person. Maybe I don't have the tools, and I'm forced to either do a single bevel prep or buy the machine, and it becomes a trade-off of money. You can weld pretty much anything you ever want to weld. If you look welding of wood on the internet, you'll find you can do it. You do it with friction welding. Now, the real problem of welding is, do you want to pay for that weld? And very often the answer is, no, I don't want to pay for that weld. I want to weld it in the easy way, the cheap way. Narrow gap welding, typical of the nuclear industry, typical of heavy wall pressure vessels. In this case, you don't even make a bevel or a V groove. You have the two walls coming up more or less parallel, and you weld from the bottom up. I had some videos there, but I'm going to move for the sake of time. Here are the parts of a groove bead. And they have kind of funny names, like most things on welding. The part of the weld you see, this is called the face. And this corner here where the face meets the plate, this is called the toe of the weld. The thickness of the weld, this is called the throat. In this case, what we have marked here is the theoretical throat or the nominal throat. But you also have an actual throat if you account for the reinforcement. Here we have the H, the reinforcement here. Around the melt area, we have an area that has been affected by the heat of welding. And guess what? This is called the heat affected zone. Here we have the groove angle, have the bevel angle. And if we look at this part of the weld, this is called the root. And the root has two things that is specified in the symbols. The root opening and the root face or the land, right? And they matter. And people who weld for real can tell you how much these things matter. But right now, for today's class, all I want is you to become familiar with the words because we will be using them a lot. In the case of a fillet weld, we also have the face, we have the toe, and this length here is what we call the leg, right? And in this case, I'm marking the actual throat, right? The length at which in which the weld projects into the plates, that is called a leg. And typically both legs are equal. Not always, but typically yes. I'm going to move through here, but this is an exam in which I asked to name all those things, and very likely the exams to come are very similar to this. Just put names to things. Interesting in carbon steel, in typical of what we do in Alberta, the passes have names. The first pass on the root is the root pass. The second pass, typically, and this is typically done with a particular type of electrode that often has hydrogen, and hydrogen is bad. So there's still advantages in using that electrode, but comes with a disadvantage of hydrogen. So the second pass is what people call the hot pass. And it's a pass typically done in a way that is going to help you drive the hydrogen of the root away. So after I did my root pass with an electrode that might have hydrogen, I do my hot passes with a low hydrogen electrode. to drive my one hot pass to drive the hydrogen away, and then I fill it up. These are the filler passes. And then you finish what is called the cap passes. And when you do visual inspection of welding, this is what you see, the cap passes. So often the welder makes sure that this is a beautiful weld right here. But in some cases, I have never seen this, but I've been told from people I believe, sometimes people can put a bolt inside the joint just to have mass and save the time in making the passes. You can imagine that that's a huge problem if that were to happen. I have a question, and the question is, if in this image, the groove angle is always 2 times the bevel angle. And of course, you can do whatever you want, but typically the answer is, if you have a bevel, you have a bevel and nothing, and if you have a V groove, the V's tend to be symmetric and to be the same on both sides. Typically, I don't know of any exception, but I'm sure if we look at it, we will find an exception. Welding positions, here. Positions in North America have names. So for the case of fillet welds, and I'm already using words that are relatively new to us. In the case of fillet welds, horizontal is when the fillet is kind of containing the weld. Flat is when the fillet is containing the weld. When the fillet is horizontal and is we weld like this, and there are numbers. For flat, we have number 1, and F means for fillet. When it's horizontal, we call it position 2, because its fillet is F. When we weld vertical, whether it's vertical up or vertical down, we call it position 3. In the case of fillets, 3F. In this case, we're welding overhead, and it's position 4, 1, 2, 3, 4. In the case of a groove, flat is 1, just as with fitted, but we call it 1G. It's a groove weld. Horizontal, position 2. Vertical, whether it's vertical up or vertical down, position 3. And overhead is position 4. For pipes, if I roll the pipe with a positioner, the position will always be what I want, which is typically flat. So this rolling the pipe in this condition is position 1. Now, if the pipe is not rolling and I need to move, that's what we call position 5. In this case, 5G, right? This is the case of horizontal. And then this position, which happens in reality, but most of the time when you see welders welding in this position is because they're qualifying. If a welder qualifies to weld in this position or with a pipe at 45 degrees, then is qualified to weld in all these other positions, to weld pipe in all those other positions. I have a question that is, what is the difference between flat and horizontal? So let's look at this schematic for a groove here. In the case of flat, the gravity is helping me, is pushing the weld down and is pushing the weld against the plate. In the case of horizontal, and I know these two terms are kind of confusing. In the case of horizontal, look at this, gravity is trying to tear my weld sideways. So while in this, the flat position, my welds tend to be quite symmetrical. In the horizontal position, the welds tend to sometimes sag a little bit in the direction of gravity, or they can have undercut, which is another new term when we weld in this condition. That was a question from an exam. It's a welder that is qualifying. There is a European system that included because it's so easy to remember. They don't call it positions 1, 2, and 3. They call it A for flat, C for horizontal. They have B for the case, for example, of fillet welds, right? Which in the case of AWS is ambiguous. E for overhead, D for fillets overhead, and then they have F and G for vertical up and vertical down. I actually think their European system is a lot better. We don't use it here, but I wanted to bring it up so easy to remember. And I think it's smarter than what we have. I want to dwell very briefly on two important quantities. So these are two terms used in welding, and which we'll be using a lot when we get quantitative, studying the mechanisms of welding. One is called T85, and this T85 is a concept that applies only to steels, and it's the time to cool from 800 degrees C to 500 degrees C. And the reason they pick those two temperatures is because the austenite decomposition, right, in nominally for the iron carbon phase diagram is at 727 degrees, right? So this, if I go fast between 800 and 500 degrees, I'm pretty much sure to have captured the phase transformation that goes from austenite into bainite, ferrite, martensite, perlite, whatever it might be. So short T85s means fast cooling, and long T85s mean slow cooling. And the other is heat input. And heat input is much like flat and horizontal, it's an ambivalent term. And people often get confused by it. When we say heat input in welding, we're talking about something that is kilojoule energy per unit length, like kilojoules per centimeter. So if you tell me a laser has so many kilowatts of power, that means nothing about heat input, right? Although people would think, oh, but this is so much heat input. Well, that depends on other things we're about to see in this slide. So in the next slide, actually. So heat input matters because it gives us a sense of a cooling rate. T85 is very directly related to heat input. If I have a high heat input, I have a lot of energy to dissipate, and it's going to take time. So T85 is going to be long. Short heat input is going to be fast cooling. So for example, if you remember stringer beads tend to have low heat input and a low T85. Weaved beads, because we can put so much energy, tend to have a high heat input and a slow T85, right? And about heat input, there are two things we should distinguish. When we calculate, we can calculate how much energy the machine gives and how much energy per unit length the plate receives. The difference between those two, or the ratio between those two, is the thermal efficiency of the process. And we'll look later, and it's tabulated, and there are ways to estimate it too. The definition of heat input is mathematics. Here is power of the heat source divided travel velocity. So power, which is energy per unit time divided travel velocity, that is distance per unit time, ends up being units of energy per unit length. In the case of arc welding, and even electron beam, but in arc welding, the nominal heat input, you do voltage times current, which is power, swatts divided the travel velocity. And of course, all this is in the metric units. These formulas we use are always metric. In Alberta, typical values are 5 to 10 kilojoules per centimeter. Good number to keep in mind. If I have a high heat input, typically means a softer weld is easier to weld, welders tend to like it because when they do the cap passes and those things, they look awesome. We tend to have less hydrogen problems. We tend to have good penetration, but high heat input also means more distortion. If we put more joules of thermal energy, we're going to have more distortion. In stainless steels and high-grade pipelines, too much heat can soften. Well, in the case of stainless steels, we can have what is called sensitization, in which we lose the stainless properties of the stainless steel. And in pipelines, we can soften the heat affected zone too much. Conversely, if we have low heat input, we would have harder welds, typically stronger beads. We have less room for error, and we can possibly have lack of penetration. I have an example here, but because of time, I'm not going to go over it now, but it's completely worked out, and you can calculate from a procedure that is proposed by Lincoln for doing, for welding this sheet. You can calculate the heat input, and you look, in this case, you look at the current, you look at the voltage, and you divide by travel velocity. And I mentioned everything is in metric. So here one of the tricks is that they are reporting the travel velocity in meters per minute, but we need to have it in meters per second. So this is a common mistake. Now we got 2.76, which is lower than what I mentioned to you, but in Alberta, we don't tend to weld 1.5 millimeter sheet. We tend to weld things that are a lot thicker, right? You must be, for the time of quiz 1, I will ask you to calculate a heat input. These last 2 slides are more part of a dictionary. Is when people talk about weld, often they mention defects, right? They mention these things like porosity or undercut. And I have these 2 slides, and I uploaded 2 sets of notes too. I want you to be familiar with what they look like. They talk about causes and they talk about cures. This is not the time to worry about that. I just want to make sure that you would know the difference between underfill and excessive reinforcement, or you would know what porosity is. The other thing is, you see that the title is discontinuities, not defects. And the reason is, in welding, what matters is fitness for service. So if I have a porosity and my code standards or client specifications deem that a certain level of porosity is not a problem for service, then that porosity, which we can call a discontinuity or an imperfection, is not a defect because I don't need to fix it. If I'm doing a nuclear power station and I find a porosity, likely I will need to remove it. And then the same porosity that before was nothing, now it becomes a defect that needs to be fixed. So it's an important concept, a subtlety, that the fact that is imperfect doesn't mean it's a defect. Very important concept in welding. I have a question about how can we obtain travel speed if it is not given in the WPS? And this is an excellent question. The WPS in general should specify the travel speed, but the welders don't have a speed meter for that. But if you give the current, you typically we're gonna see from all the mechanisms of welding, if I know the current, I know how much metal I'm putting down. And if we say what this cross-section of the weld should be, or the reinforcement, or the size of the groove, essentially I'm giving a cross-section of material that we need to fill. And the welder can look at that with the eyes. So even if we don't tell the welder how fast to move, there's so much metal coming from the electrode and so much metal that needs to be filled, that there is only one velocity that makes that possible. And even if it is not written, the welder will reach more or less that velocity quite well. And actually, even if you say what velocity they should go, the welders will do this mechanism in which there is a balance between mass and of mass of the electrode coming back out and mass being put in the weld. All right, so I have 15 minutes now, and I'd like to move into welding symbols. Okay, let's see.